Hey everyone, my name is Ben and I do developer relations at Gelato. In this video, I'll be presenting something built on top of Circle's CCTP, which is gasless and automated CCTP powered by two of Gelato's services, namely Gelato Web3 functions and also Gelato Relay. This video will be split into three parts. First, I'll go over some slides to give a high-level overview. Then I'll do a live demo in which we gaslessly transfer USDC from Avalanche to Arbitrum. And finally, I'll do a walkthrough of integrating the CCTP SDK that we provide into a TypeScript Node.js project. First of all, what is CCTP? CCTP is Circle's cross-chain transfer protocol, and it is a permissionless on-chain utility that facilitates USDC transfer between blockchains via native burning and minting. So it's essentially a bridge for native USDC, but unlike traditional bridges, there's no need to lock up tokens on a source chain and then mint synthetic tokens on a destination chain. Rather, we can directly burn USDC on the source chain and then mint native USDC on the destination chain. And this also unifies liquidity because we no longer have synthetic tokens, and we also don't have tokens locked up and fragmented across multiple chains. So how does CCTP actually work? There's 3 steps involved. The first step is burning USDC on the source chain, which emits an event called message sent. In the second step, this event is observed by Circle and an attestation signature is issued. And we can fetch this attestation signature from the attestation service API and use it to mint USDC on the destination chain, that being the third and final step. And this is really cool, but there are some limitations. For example, steps 1 and 3, so burning USDC on the source chain and minting USDC on the destination chain, both require transactions on each chain respectively, which means the user requires native tokens on both the source and the destination chain. So if an Ethereum native user is migrating to Avalanche, they would have to acquire AVAX in advance in order to execute the second transaction, which mints the USDC. And this introduces quite a bit of friction for the user. In addition, subsequent transactions on the destination chain also require native tokens. So even if we're able to transfer USDC from Ethereum to Avalanche, we still require native tokens on Avalanche to continue interacting or transacting with this USDC. And last but not least, the second step, so waiting for this attestation signature, can take up to around 15 minutes, and the user has to wait for this attestation before manually issuing the mint transaction on the destination chain, which introduces quite a bit of waiting time for the user. The bottom line is that whilst USDC is free to move around chains, the native tokens required to interact with it are not. The vision is that we'd like to be able to move USDC between chains and cover the associated cost of this transfer using the USDC being transferred itself. We'd also like to pay for subsequent transactions on the destination chain using the same USDC. And ideally, this whole process would be automated reliably in the background, so the user can just hit a single button and the USDC is transferred from, for example, Ethereum to Avalanche without requiring ETH or AVAX in the user's wallet, and also without requiring further user interaction. So without having the user wait for this attestation signature and manually issue this final mint transaction. And eliminating this dependence on native tokens gives us infinitely more freedom, with the implications being that USDC now acts as an interoperability layer, connecting multiple chains, and we also eliminate the need for per-chain native tokens from a user perspective. And all of this is actually already possible using our new gasless CCTP SDK, which allows developers to super easily integrate these gasless cross-chain transfers into their new or existing projects. So bridges can implement this SDK to support gasless USDC transfers, and actually any dApp can implement this to allow for USDC payment across chains. An example of this could be an NFT marketplace on Avalanche, which wants to support USDC payment from Polygon or Ethereum or Arbitrum, all whilst remaining Avalanche native. And this SDK is available on GitHub at github.com/gelato-digital/gasless-cctp-SDK. Implementation is as simple as importing the SDK and calling transfer. Transfer expects the owner account address, so the address of the EOA that we're transferring the USDC from, on the source chain and transferring the USDC to on the destination chain. It also expects the total amount of USDC to be transferred, including the associated fees both on the source chain and on the destination chain, which can be specified. So the next arguments are the source chain max fee and the destination chain max fee, and these are maximum amounts, so what is spent is likely much lower than this. The next arguments are the source chain ID and the destination chain ID, so which chain we're transferring the USDC from, and also which chain we're transferring the USDC to. And finally, we pass in a callback function, which allows the SDK to sign any type data. So the caller determines how this data should be signed, which gives developers a lot of flexibility. For signing, we can use ethers or Web3.js or Veeam or some custom implementation. And at the same time, the caller is notified whenever a signature is requested, which allows for a front end to make UI updates and also to do custom error handling. Now, before we jump into the demo, I'll quickly go over the flow. So in addition to the Circle CCTP contracts, which are token messenger and message transmitter, we also introduced two intermediary contracts called Gelato sender and Gelato receiver. All these are responsible for is paying for the transaction fee using some of the USDC being transferred, and they also accept ERC-3009 signatures so that we can approve USDC transfer without requiring an approved transaction on-chain, which would otherwise require native tokens. And since CCTP is omnidirectional, so we can transfer USDC from any chain to any chain, both of these contracts are deployed on each network. So the Gelato sender and the Gelato receiver are both deployed on Ethereum, and the Gelato sender and Gelato receiver are also both deployed on Avalanche. So let's imagine a transfer is requested using the CCTP SDK, and this can be done by a user on a front end or programmatically on a back end. The SDK will prompt the caller to sign the required signatures and then put a transaction on-chain using Gelato Relay. On-chain, the Gelato sender will use one of the signatures to receive the user's specified amount of USDC and sends a portion of this to a fee collector to cover the transaction costs. The rest is forwarded to the CCTP token messenger, which proceeds to burn the USDC. Both of these contracts then emit an event, message sent and deposit for burn respectively, which a Web3 function is listening for. The Web3 function indexes these events and periodically calls the attestation service to fetch an attestation signature around every 30 seconds. And once an attestation is issued, a transaction is relayed on the destination chain, again using Gelato Relay, and this calls the Gelato receiver. On-chain, the Gelato receiver uses the attestation signature issued by Circle to mint native USDC directly to the user's wallet. And since the USDC goes directly to the user's wallet, we use the second ERC-3009 signature to transfer a small fee amount from the user's wallet back to the Gelato receiver contract. And this allows for us to cover the transaction fee. It's also worth noting that the Web3 function does a little more than this. It verifies that transactions have successfully executed at every step of the way, and it reattempts any transactions that have failed. A second thing worth noting is that since Gelato never takes custody or ownership of the user's USDC, the user can always interact with Circle's CCTP contracts directly to mint or claim their USDC. For example, if a user uses the SDK to initiate the transfer, they can always manually redeem the USDC at any point themselves. They don't have to go through any of the Gelato contracts or through the Web3 function. So with that out of the way, let's see it in action. And this example front end is available on GitHub at github.com/gelatodigital/gasless-cctp-frontend. And it serves as a nice implementation reference. This is the demo UI, and as we can see, the code for this is not yet audited by a third party. So if you do want to test this out for yourself, please bear this in mind. At the top, we can select which chain we'd like our USDC transferred from, and which chain we'd like our USDC transferred to. And below this, we can specify the total amount of USDC we'd like transferred. Now, before we do this, let's first check out our account's balance on MetaMask. On Avalanche, we have 0 AVAX, so no native tokens in order to transact on the network, but we do have 10 USDC. And on Arbitrum, we have 0 ETH, so again, no native tokens to transact on the network, and we have 0 USDC. So in this demo, we'll be transferring the total amount, which is 10 USDC from Avalanche to Arbitrum. On the UI, we specify Avalanche as the source chain and Arbitrum as the destination chain, and the total amount of USDC when transferred is 10. This includes the fee amounts both on the source chain and the destination chain, which can be seen below. It's worth noting that these are absolute values, so whether we transfer 10 USDC or 1000 USDC, these will remain constant. Also, these are maximum fee amounts, so what we'll end up spending is likely much lower. Below this, we can see the minimum amount of USDC we're due to receive, given these fee values above. So let's initiate the transfer. First, we're prompted for an authorization signature on Avalanche, which approves spending of our 10 USDC. Then we're prompted to switch to Arbitrum so we can sign the second signature. And this authorization signature again allows spending of USDC, in this case on Arbitrum, in order to cover the transaction costs. So this is 1 USDC, the max fee amount we specified on Arbitrum. And finally, we switch back to Avalanche to sign a final ERC2771 signature, which enforces our max fee intent and also our destination domain intent. So this removes any trust assumptions since we've signed off on all the data that will land on-chain. And now the transfer is initiated. So we can leave the page, or I can even turn my PC off entirely, and a Web3 function will continue to automatically process the entire transfer in the background. As we can see, the USDC has left our wallet on Avalanche, and it just arrived on Arbitrum. The entire transfer took around 1 minute, and all of the transaction costs were covered using the USDC being transferred itself. So we transferred 10 USDC initially, and we receive around 9.5 USDC. So 0.5 USDC was used to pay for the gas fees both on Avalanche and on Arbitrum. This final portion of the video will be a walkthrough of integrating the gasless CCTP SDK into a TypeScript Node.js project. And this process will be the same whether integrating into a front-end app or a back-end. The SDK can be used in any environment. I've created a new directory for our demo app and opened it in VS Code. So the next thing we'll be doing is installing the required dependencies. And since we're writing this in TypeScript, the first dependency we need is TypeScript itself. So let's install that. In this case using yarn, but you could also use npm if you prefer. We'll also install something called tsnode, which allows us to super easily run the TypeScript without having to compile it to JavaScript manually each time. Let's also install the CCTP SDK, which is available on npm at Gelato network /CCTP-SDK. And we'll be using ethers to create wallets and using those to sign the payloads. So let's also install that. And finally, we'll be storing the private key associated with the wallets in a .env file. So let's also install .env. The next step will be creating our .env file and populating it with our private key. And this is the private key for the wallet that you'd like to cross-chain transfer USDC from. And be very cautious with this private key since anyone with access to it can transact on your behalf and steal any funds in the wallet. So I'll populate this with my private key off screen. Now let's actually write our code. We will store our TypeScript in a source directory and call it index.ts. We'll create a main function, which is asynchronous. And for now, we'll just console log hello world. And make sure we call this from the outer body. Now let's make sure this works. We'll run yarn tsnode and specify our source directory. This will automatically resolve to the index.ts file. So we see hello world. And this works, but to save us some time in the future, let's create a script for this. This will be a start script, and it will simply run exactly what we just ran. So let's test this out. Instead, we can simply write yarn start, and this again prints hello world. Logging hello world is nice, but ideally we'd like to cross-chain transfer some USDC, so let's implement that now. The first thing we'll do is read in our private key from .env. To do this, we will import .env. And initialize it. We'll then read in the private key. And we also want to make sure this is populated. If not, we'll just throw an error message notifying the user. Next, we'll create an Ethers wallet using this private key, which we'll later use to sign data. And the Ethers wallet just expects a private key. And finally, we call the transferred method, which we import from the CCTP SDK. This expects the owner's address, which in our case is the address of our wallet. It also expects the amount of USDC to be transferred. Previously, we transferred 10 USDC from Avalanche to Arbitrum, and in this demo, we'll transfer the remaining USDC from Arbitrum back to Avalanche. And finally, we pass in a callback function to sign type data. Now let's quickly check out the SDK to see what this function should look like. We see that the iSign function has the following signature. It takes the domain, types, and values as arguments, and it should return a promise string. So let's copy this. And type data domain and type data field are both from Ethers. Now to sign this, we'll just use the Ethers wallet. So we can do return wallet.sign type data, passing in the domain, the types, and the values. And this works perfectly fine, but there's actually a more compact way of writing it by forwarding the arguments directly to wallet sign type data. And this is possible because the callback function and wallet sign type data both share the same function signature. We also need to make sure to bind the this pointer. If you'd like to find out more about this, feel free to search up JavaScript bind. And that's all there is to it. The whole implementation is only a few lines of code. So let's try it out. This executed successfully, so let's check our wallet's balance. On Arbitrum, we see that we now have 0 USDC remaining, and we'll wait for this to arrive on Avalanche. The USDC just arrived on Avalanche. It took around 15 minutes since we had to wait for block finality on Arbitrum before the attestation signature was issued. And again, we didn't require any native tokens, so no AVAX or Ethereum, and the entire process was automated in the background, whilst only requiring a few lines of code for the implementation itself. And that concludes gasless and automated cross-chain transfers. I think this provides a really nice user experience, and I'm super excited to see how projects will integrate this in the future. Thank you so much for your time.